Last part of Unit 3 review, we've got orbitals and quantum numbers. We are not doing calculating quantum numbers where, like, if n is 3, then L is 2, and m sub L. We're not doing those. We're down to the bare minimum on what we need to do for the final. Again, I'm trying for big ideas on the final, not little picky things. So here's what you need to know. First part's big. The difference between an orbit and an orbital is that orbits are flat, orbitals are 3D, orbits gotta have electrons, and orbitals are where they're likely to be found. Schrodinger's quantum model talks about orbitals, and you know that in life, things are not certain, things are likely. Probability is a big thing, and orbitals are based in probability, where the electron's probably gonna be. And that's way better than saying it's flat and it's always here. Every orbital can hold 2 electrons. The reason you're going to see different numbers for P, D, and F coming up is because there are more than one of those orbitals working together. So orbital, how many electrons? 2 at most. That's huge. Guarantee that's a question on everything, because it always is. We talked about 4 quantum numbers. N was your energy level, and I've got this diagram up here to remind you. N can be from 1 to 7. We're using that chart. We need that chart. So for L, being the shape of the orbital, and this is why we need that chart. Some of you can probably still write configurations without it, but it reminds us that our N's are 1 through 7, and that our L's, our shapes, are S, P, D, and F. Put those up there, and they're S, P, D, and F. Remember, Steve's poop doesn't float. I haven't had to say that since like October. Steve's poop doesn't float. Silly penguins don't fly, whatever you want to say. So remember, if you want to talk about an orbital name, this is how you name them. You put your number that's N, and then you put your letter that's the shape, that's L. So if I have a third energy level D orbital, it's 3D. And check this out too. There's no such thing as a 1p orbital. There are no such things as 1d or 2d, or 1, 2, or 3f. We skip one down each time. So, my number of orbitals comes from how many directions they can point, and you do not need to be able to calculate these, but you need to be able to know these, that I have 1 s orbital, I have 3 p orbitals, I have 5 d orbitals, and I have 7 f orbitals. And that's going to let me figure out how many electrons I can hold total in these, because if each one can hold 2 electrons, my s can hold 2, and my p can hold 6. 5 times 2 puts 10 in the d orbitals, and 14 in the f. But I don't think you're going to be using those big ones too often, because remember, I'm trying to get the final in not too long of a time. See if you know something without seeing if I can trip you up on long questions. You will need to know the 2 numbers for m sub s, the spin of your electrons, and it's just plus 1/2 minus 1/2. So if you look for fractions in positive, negative, just put in your brain that it's a fraction, and it should help you remember the spins. Electron configurations. This is big. This is a big concept from this chapter, and a lot of you were getting really good at it by the time we were done. You won't need to remember the names of the rules that go with them, but you're going to need to use them. Like the Aufbau principle says, fill from lowest energy to highest energy. Okay, when I use this chart, it automatically does the Aufbau principle for me. Or if I read across the periodic table to go in order also, it does it for me. Pauli exclusion just says that they have to have different spins. Okay, cool. And if we were to draw orbital diagrams, Hund's rule would partially fill each. We won't be drawing the diagrams on the test because you can get the same idea from the configuration. You would need to know, though, that 2 electrons in the same orbital have to have opposite spins. That's a good fact. And you'd need to know that if you've got orbitals of equal energy, you partially fill each before you completely fill any. It makes it balanced. That's the whole goal. So if I've got a set of p orbitals, and I want to put in 4 electrons, I don't pile up 4 and 2 of them. We share nice. Everybody gets a piece of pizza, and then the first kid that's hungry gets the other one. Remember, the arrows point opposite direction to show opposite spins. So back to this chart that helps us remember our order of orbital filling, and I am probably going to have to eventually steal my nicely drawn orbitals there. When we draw the arrows for the order, if you're doing this way, not on the periodic table, remember, I hit 1s first. The arrows come down at an angle. They don't go straight down. They go down at an angle and connect. I don't think we're going to need any more than that. I think we should be good. That's a lot of electrons right there. And we're not, again, doing the biggest of the configurations I can think of. So we're going to work through these. I put some examples in your packet. We're just going to combine, because we've been doing this before, we're going to combine working with electron configurations and noble gas configurations all at once. We've got some steps in your packet for you. Find the element's atomic number. You're using the whole number. We start with 1s and we fill them up and we subtract. So if you look at the example I did for phosphorus, it's already written out for you. It's number 15, so we've got 15 electrons. Following the chart tells us 1s fills first and s can hold 2, so 1s2. I have 13 left because of 15 minus 2. Next is 2s, so 2s2. I have 11 left. I work through the examples, and I subtract until I get down to 3p. It can hold 6, but I only have 3 electrons left. I don't write 6, I write 3. I write how many it actually has, and I double check, because the superscripts, little numbers up top, add up to 15 if I did it right. So 1s2 plus 2s2 is 4, plus 2p6, that's 10, plus 3s2 is 12, plus 3p3 is 15. Add them up. Now for a noble gas configuration, and I'm doing another example of this. You have this example in your packet, plus I'm going to do at least 1, maybe 2, maybe 3 with you before I turn you loose on your own. When you're using a noble gas configuration, you always go to group 18. I got the list in the packet, and we match them up with the last full p orbital, p6 of some kind. In our phosphorus example, 3p wasn't full. It wasn't 3p6. So I go back to 2p6, which corresponds to neon. It matches up to neon. It's the second one down. Neon in brackets, 3s2, 3p1. Awesome. So I'm just going to I think I have room to put up a couple of these down here. We'll do sodium, we'll do chlorine, and we'll do scandium. We'll do the first 3 on your practice. If you want to try them on your own and check, or at any point, feel free to pause. I'm going to put them right here. In fact, you know what I'm going to do? I don't think we're using the F orbital at all in your practice. So if I take that out, I got plenty of room. Let's start with sodium. And you don't have to keep the tallies I do. I'm going to do the noble gas and regular configurations together and call this a day. So sodium. Sodium's number 11, so I need 11 electrons. First one, 1s, it can hold 2, so I give it 2. 11 minus 2 is 9. I'm writing my little numbers below that are how many I have left. I don't care if you do. That's the nice I don't care, not the mean I don't care. If you don't need to, you don't have to. If you want to do these on a calculator and subtract as you go to keep the tally, feel free. 1s2, I'm out of arrow, so I go to the next arrow, and it's 2s, 2. 9 minus 2 is 7. 2p holds 6, because I have 3p orbitals, yeah. So I do 2p6, s is 2, p is 6, d is 10, f is 14. 7 minus 6 is 1. So that means 2p, then 3s, and sodium is done. 2 plus 2 is 4, plus 6 is 10, plus 1 is 11, which I wanted. Great, my superscripts add up, and if you look for sodium, it's in the first row of the S block, all the way over at the left, third row down. I'm not making you learn those, but if you knew that in the fall, remember, you can check where they are. Now for my noble gas configuration, I want P6. Biggest P6, which is here. I count down 2 rows on the periodic table. helium, neon. So 2p6 is neon, Ne, and I rewrite the rest 3s1. So here I've got that example showing you 2 plus 2 is 4 and 6 is 10. My video might cut out. I just got my startup disk is full, but I'm going to keep going. And if it fails, you've got this example at least. For chlorine, what's nice is I know chlorine is 17, and I've got the same startup on these. My orbitals are always going to fill in the same order. How about that? What I've used here, 2, 4, 10, 12 electrons already, and I only have 5 more to put in to give me the 17 I need. 2, 4, 10, 12. Chlorine would be 17, so after 3s, I'm out of arrow. Let's go up to 3p. It would take the last 5. But I can't use that for my p orbital, my full p orbital for my noble gas. It isn't full, it isn't 6. So I'm back at 2p6 again for neon in brackets and for the remainder written after. I think I'm out of disk space. I can't show you scandium, but I'll give you a hint. It ends with 3d1. I'll put up the answers to these the next time, and I'll put them up in material. If you need any help on them or you want me to go over any more, please let me know. Have a great day. Oh, and do your practice. Do the rest of them.